In this video, we'll quickly walk through the homework so that you have a good idea of how to approach each of the exercises. So the first exercise, implement a function x per multi-additive division, which takes 3 positional arguments a, b, c, and returns the result of this term here. And the computations should be done element-wise. That's not a constraint, but something NumPy is doing by default, so you don't have to really worry about that. Same for this here, make sure that your function performs automatic broadcasting when required. If we use the default operators and NumPy functions, then this should not cause a problem. So for example, to start, we can compute exponents by simply writing np.exp, and then we put in that brackets the a times and then so on. Okay, for the next exercise, strange pattern. Just to be sure you know what the pattern is about, so we want diagonals, and we want them to be spaced out by 2. So one diagonal, 2 spaces, another diagonal, and such that they fill the whole array. And the array should be a Boolean array, meaning our x's evaluate to true, and the blanks are false. So to give you an idea of how to approach this exercise, you could initialize an array that is all false and has the according shape nm, and then you can build up the x's row by row. So you go in the first row, you place an x at the first spot, then you leave 2 spaces, place another x, leave 2 spaces, and you do that until you reach the end of the row. And then for the second row, we don't start at the first, but at the second spot, then do the same thing. Then for the third row, we start at the third spot. And now the tricky thing, for the fourth row, we also start at the first spot. And now speaking in terms of indices, for the indices 0, in terms of row, we also start in column 0. And then here 1, 1, 2, 2. And now here we go back to 0. And there is one operator that can achieve this kind of pattern. So that 0 is 0, 1 is 1, 2 is 2, but 3 is then again 0. And to give you a hint, it has something to do with division. Okay, next up, dimension reduction. So here we started with an array that has at least 2 dimensions, and then we reduce the first dimension to its sum. So let me quickly illustrate. So we import NumPy as np, and then we print np.once. Let's choose the shape 2, 3, 4. And now what it means to sum across the first dimension means we sum the elements of the first dimension. So we have here in the first dimension 2 elements. So these 2 elements, and summing them means we add these together. And that can be simply done with calling np.sum, but we have to specify which dimension or which axis we sum across. Okay, and then the second part is then passing this summed up array to the median function. And there we now don't use the first dimension, but the last dimension. So we can again pass some dimension axis argument to the median function. And then finally we calculate on this median array the standard deviation. So the array goes into the sum, into the median, and then into the standard deviation. And of course it doesn't go into these functions separately, but we take the result of the sum, put that into the median, take the result of the median, put that in the standard deviation, which there's also a NumPy function for, and then we return that value. Okay, finally, interpolation. So here we are given a list called n, and it contains n values. Let's say 2, 3, 4. And then we have a step size called n steps, which in the task description is 2. And now we have to create a new array based on these 2 values. And the length of that array is also given in the exercise. And this length here is not really a constraint, but it will emerge organically. So our new array should also contain all of the original values, but with a difference of step size. So we start with the first element, then we take another step. So the first element is already considered step 1. Then we take step 2, so second element, and then the third element should again be a value from the original array, so the next one. And then again, this is the first step already. We take a second step, and then we have again the element from the original array. And in between these arrays, we interpolate linearly. So we write 2.5, which is equally spaced between 2 and 3, and here 3.5. And for this interpolation, there is a NumPy function which can create this linear spacing. And so how we would go about solving this exercise is that we would loop through this list here and then take the original elements and then interpolate between them. So you'd take the 2 and 3, then create the interpolation, then go to 3 and 4 and also create the interpolation. Using this approach, we consider the 3 2 times. So first for this interpolation and then for this interpolation. And this could lead to duplicates. And so what we can do is that we interpolate from 2 to 3, but we exclude the 3. And then we start with 3, interpolate to 4, and then we would also exclude the 4 if it was not the last value. So we had a 5, for example. So we would go from 3 to 4, exclude the 4, start from 4, and then we go from 4 to 5, and then also add the 5 again. And so now let's consider the length of this new array. So we do the interpolation for every element except the last one. So from 2 to 3, 3 to 4, 4 to 5. That means we interpolate n minus 1 times. And then we also add the last element. So we interpolate n minus 1 times, and now the question is, what's the length of the interpolation? And let's call it interlength. And we see how this matches with the array length that is given in the exercise. And so that tells us that the interpolation length should be equal to the step size. So when we interpolate from 2 to 3, that should have length n steps. And that's also what we see in the example. So interpolating from 2 to 3 has 2 values, so length 2, which is matching with the step size. And then going from 3 to 3.4 is again 2. And then we have the last element, which is our +1 here. To not lead you on a wrong track, when we interpolate between 2 and 3, these two values will be already included when we specify how many values you want in our function. So maybe we have to take the step size +1, such that when we cut off the right side element, we are then left with our n steps elements. So the function maybe gives us 2, 2.5, 3, and then we take only 2 and 2.5. Okay, with that, you hopefully have an easier time going through the exercises. If not, you can visit the coding support on Monday, and it doesn't matter at which point in the homework you are, as long as you bring enough time, we'll make sure you pass.